So, hello, I hope you're all doing well. Today we continue with important topics for our cosmology class. An important topic that we're going to introduce right now is the metric of space-time, a concept from general relativity. We will need this in this class for several different things. One reason is to understand better how photons propagate in the universe. This will be very useful to better understand, and also to better define distances in cosmology. We will see that there are a couple of different distances in cosmology that can be defined in different ways and which are very useful to determine the cosmological parameters. And for this reason, we need to know about the metric of space-time. And we can start this discussion by analogy and by what we know from our three-dimensional flat space. In flat space, we know that in the Cartesian coordinate system with coordinates x, y, z, the distance delta s squared is given by the sum of the differences in the coordinates. It's basically we have delta s squared equal delta x squared plus delta y squared plus delta z squared. It's very simple. It can also be written in a differential form. So we have ds squared equal dx squared plus dy squared plus dz squared. We can in principle change our coordinates. This has nothing to do with geometry. This is just to do with the choice of the coordinate system. For instance, we can always use a spherical coordinate system to describe our points from the point of view like of a central particle, for instance. And if we do that, we can express the Cartesian coordinates through the spherical ones. We have x equal r sine theta cos phi, y equal r sine theta sine phi, and z equal r cosine theta. And it can be done also the other way around. We can express the spherical coordinates through the Cartesian ones. We have r equals square root x squared plus y squared plus z squared. We have cosine theta equals z over r, and tangent phi equal y over x. And using these relations, we can in principle always transform back and forth between those coordinate systems. So we can use both of them if we want, and it depends on our preference if we use the Cartesian or the spherical coordinate system or even another one. Now we can also define differential line elements in the spherical coordinate system. It depends now if we consider displacements in a particular direction. For the Cartesian system, this is very simple. As a displacement in the x direction is just dx, a displacement in the y direction is just dy. For the spherical one, it's a bit more complicated. If we have a displacement in the r direction, in the radial direction, then the displacement also is just given as dr. But if you have a displacement in the theta direction, the displacement in this case is r d theta, because of course the displacement has to be a length scale. It needs to have a spatial dimension. That's why we multiply with the radius. And if we consider the phi direction, in the phi direction, it's the same. We have to multiply with the radius to obtain a spatial dimension. And we also have to multiply with sine theta, because the phi angle is projected on the xy plane, and we have to consider the projection on the xy plane. That's why we multiply with sine theta. In that way, we can define the differential line element. Another quantity that we will need is the differential volume. The differential volume in principle is just now the product of all the three differential line elements that I mentioned. So we have to multiply dr with r d theta, with r sine theta d phi, and then you will obtain the expression that is given here at the bottom. Yeah, what you can also do is, of course, yeah, you can express not only the differential volume, but also the total displacement can be expressed in these spherical coordinates. And the way how to do that in principle is analogous to the Cartesian one. I mean, in the Cartesian one, you recall that you just sum up the squares of the different displacements in each individual direction, and you obtain ds squared. You can do the same thing in the spherical system as well, because the spherical system also has an orthogonal basis. The unit vector in the r direction is perpendicular to the unit vector in the theta direction, and the unit vector in the phi direction. They're all perpendicular to each other. So we can say ds square is equal to the r square plus r square d theta square plus r square sine theta square d phi square. And good, if you want, you can slightly rephrase this expression and write dr square plus r square, and then in brackets d theta square plus sine theta square theta d phi square, where here the expression in brackets basically corresponds to the contribution that corresponds to the solid angle that is being covered. So far so good in principle. What we can also consider and write down relatively easily, you perhaps haven't seen it in exactly this way yet, but if we now assume we have a flat and also uniformly expanding space, it's relatively simple to write down a line element for a flat and uniformly expanding space. You just take your usual Cartesian line element, dx square plus dy square plus dz square. And if you want to add expansion in a uniform way, then the expansion only depends at time. So it must be a factor a that only depends on the time coordinate. And we can just write it as it's given here. So we have some factor a square of t that we put in front of the sum of the squares. And in that way, the function a will determine how our line element is expanding over time, how it either grows or shrinks. And the dynamics of a of t decides how all the scales are changing in the universe. So, it's a principle quite straightforward. The meaning of the dx, dy, and dz coordinates in this expression here is then exactly the meaning of the co-moving coordinates that we introduced earlier, because these dx, dy, dz coordinates, these will be fixed, and the value of a will tell us how a certain co-moving distance or co-moving length scale will relate to an actual physical distance, because ds is our physical distance, which is changed here by the scale factor. And of course, we don't have to write this in Cartesian coordinates. It can be written also in spherical coordinates, which is done here in equation 11. So here we just replace dx square plus dy square plus dz square with the expression from the spherical coordinates the same way as we did it before. And that still corresponds to a flat space-time. The only thing we've done here is change our coordinates. Now, if we go from here to general relativity, then it becomes a bit more complicated, because in general relativity, space and time, they receive a unified treatment. So we do not just consider the spatial part of the metric, we have to consider the space-time metric, g mu nu. And for this purpose, we have to sum up over the indices mu and nu from 0 to 3. 0 is the time-like index, 1 to 3 are the space-like indices. And the metric or the metric matrix is g mu nu, and it's multiplied here with dx mu and dx nu, which are basically yeah, the space-time components of the displacement. So dx1 to dxv are basically our usual coordinates x, y, z. Dx0 is the time component. You see here that in principle you have you can have very complicated expressions, which can also include mixed components. So you can have components in your metric where you combine, for instance, dr d theta, dr d phi, or dr dt. You can have mixed spatial components or mixed components between time and space. So you can have all kinds of combinations here in principle. Good, that's something that we also have to take into account for cosmology. Even though in cosmology we have the benefit that the solution has to be homogeneous and isotropic, and that's why the solution from GR will simplify. It simplifies a lot actually, and what we obtain is the expression that is given here in equation 13, where we have ds square equal minus c squared dt square plus a square of t, and then in brackets here an expression that is very similar to what we had for the case of spherical coordinates, but it's more general here. We have dr square divided by 1 minus kr square plus r square d theta square plus sine square theta d phi square. Yeah. So what you notice is that the first term here is somewhat different. If we adopt the case with k equals 0, then we obtain our expression for the flat geometry, the flat universe, and we have then the same expression that we were having before for the space-like component. If instead, if k is equal to 1, that corresponds basically to the spherical geometry with the closed universe, and k equal to -1 is the open universe. And the other metric that we see here, that is a special metric which has a name, it's the so-called Robertson-Walker metric, or sometimes Friedmann-Robertson-Walker metric of cosmology, and k is the curvature parameter that we've been introducing before. So.